Right now, in cutting-edge laboratories all around the world, advanced machines are actively printing living human tissue. Instead of melting plastic, these printers use bioink, a precise mixture of living human cells suspended in a protective water-based gel called a hydrogel. Here, the printer needle deposits hydrogel directly into a support bath to build the structure layer by layer. Once the architecture is set, the tissue is held at 37 degrees Celsius, where the cells communicate and fuse together. As the cells multiply, they eventually consume and replace the temporary hydrogel scaffolding with their own natural matrix. The printer provides the physical blueprint, but the final integrated tissue is the result of natural biological assembly. This technology is already being used to create flat, simple tissues like cartilage, corneas, and skin for surgical use. One of the most advanced applications is a mobile skin bioprinter that can be wheeled to a patient's bedside to scan and map the exact topography of a burn wound. The printer deposits all 3 layers of human skin directly onto the injury, which has been shown to improve wound closure and reduce the scarring associated with traditional grafts. While these successes are changing surgical outcomes, flat tissue represents only the most basic structural level of the human body. If we can print skin, why are millions of patients still waiting for heart or kidney transplants? The obstacle is vascularization, the need for a network of microscopic capillaries to deliver oxygen and filter out waste. Skin is thin enough to absorb what it needs from its environment, but in a thick organ, the cells trapped in the center will suffocate and die without a dedicated blood supply. Look at this 3D vascular tree model. The engineering hurdle is soft hydrogels often collapse when printing hollow tubes as small as human capillaries. Scientists use thermal flow mapping to verify fluid moves through these printed branches without leaking. For an organ like the kidney, which contains 1 million specialized filtration units called nephrons, the level of detail required exceeds what manual placement can achieve. Printing a complex whole organ is currently impossible because we haven't yet mastered the engineering of self-sustaining multi-scale plumbing. To bypass the need for blood vessels, researchers are printing organoids, tiny, vascular-free clusters of human cells that function like miniature organs. These mini-organs are already being used in pharmaceutical laboratories, replacing traditional petri dishes and animal models for drug testing. Currently, about 90% of new drugs fail in clinical trials because animal models often fail to accurately predict how a human will react to a specific toxicity. This bioprinted liver model shows why organoids are more effective. By arranging hepatocytes and endothelial cells in a 3D environment, researchers can observe how diseases like liver fibrosis actually progress in human tissue. While organoids aren't meant for transplantation, they are saving lives today by identifying toxic medications before they ever reach a human volunteer. The current state of bioprinting focuses on flat tissues for grafts and organoids for pharmaceutical research. In the next 5 to 10 years, we expect the development of partially vascularized tissue patches to repair localized damage in organs like the heart. The long-term objective of this field is the creation of fully transplantable, complex whole organs. These images show the transition from a digital blueprint to a cellularized heart construct. Moving from flat skin to a 3-dimensional heart is a process strictly gated by our ability to solve the microscopic plumbing of the human body. We don't need fully printed hearts to see that 3D bioprinting is a medical success. The ability to manufacture tissue layer by layer is already healing wounds and accelerating our understanding of disease. A replacement heart is a distant milestone, but the capacity to biomanufacture life is already providing clinical solutions that were impossible a decade ago.